Okay, let's get started. So welcome everyone to another lecture as part of our ID 5130 parallel scientific computing course. Okay, so in the last lecture we finished discussing about the numerical methods using OpenMP, right? So in today's lecture we're going to start the next chapter, that is chapter 4. This is MPI programming, that is message passing interface, okay, which stands for MPI, stands for message passing interface programming. Okay, this can also be thought of as programming on distributed memory machines. Okay, so this is distributed memory programming, right, with MPI. So till now with OpenMP we looked at shared memory programming, right? So today onwards we're going to look at distributed memory. So as you recall, we talked about shared memory machines and distributed memory machines. So in distributed memory machines you have basically several CPUs, right, or cores, right? And then yeah, so if I were to draw these as the CPUs or core, right, so we have several CPUs or cores, right, and each core has its own essentially RAM or memory, right? So this is the memory associated with each of these cores, right? So this is the corresponding memory for each of the cores, right, which can be accessed by the CPU, and all of these, right, are connected, all the CPUs are connected through an interconnect. Okay, that's what we have discussed. Right, so however, this memory that we have for a particular core is only directly available for that particular core. Okay, so that means the memory is only directly accessible, right, by that particular core or CPU, right? So it is not accessible by other cores, unlike a shared memory machine. Okay, so that's kind of what distinguishes a distributed memory machine from a shared memory one. And if you look around, all the clusters, all the high performance clusters are built on a distributed memory architecture like this, right, as we discussed before as well. Okay, however, each of these CPUs might themselves have several cores again, right, in which again a shared memory like a program can be run, or you can even run or write programs which are kind of hybrid. In a sense, you can run a shared memory and a distributed memory program within which a shared memory kind of behavior can be obtained. Okay, so such things we are not discussing in this course, but we will only discuss the pure distributed memory programming using MPI, which stands for message passing interface. Okay, so essentially each of these essentially a program running on a particular core or a CPU is also referred as a program running on a particular CPU or a core is referred as a process. Okay, so this we will be using as a terminology, and two processes can communicate with each other by using send and receive commands. Okay, send and receive function calls hello two or more processes to communicate with each other. Okay. Okay, so essentially now all these, how the process can send or receive data or other information is all implemented using message passing interface, which is essentially MPI. We will be learning, and MPI itself is not a new programming language. Is not a new programming language. Rather, MPI, just like OpenMP, is basically a library that contains a set of functions, right? Data types and other required functionality, which will allow a user to write a program that can be run on a distributed memory machine. Okay. So, all right. So essentially, all these libraries are available, at least as far as the course is concerned. These are available as an extension, right? And these can be called from standard C, C++, or Fortran programs. Okay. All right. So that's about quickly about MPI, and we will be learning about these, the send receive kind of pair of communication function calls, as well as we are also going to learn about some global communication. That means it involves more than two processes, okay, and which is also known as collective communication. Okay, all right. So let's get started by looking at a sample program. So of course, the first program we will look at is the Hello World program. Which we already saw in the context of OpenMP. I'm going to just show you a Hello World program in C, which is of course very straightforward, which you can easily relate. Okay, so here I show a Hello World program. This is rather very small, so you just have hash include stdio.h, and then you have the main program, and then which basically prints Hello World and it returns 0. Okay, so if you just compile this gcc program hello.c, and then /error will print hello world. Okay, so this is very simple. Now the idea is we can convert this particular hello world program into a parallel version. Okay, or rather we would like to do this using implement this hello world program using MPI. Okay, that means what we want to do is unlike OpenMP, where we said we would like to just print hello world from each of the process or each of the thread, right? Here we want to do something little more, and that is nothing but let us try to designate out of the processes that we have. Let's say if we have several processes 0, 1, 2 all the way to p-1 processes, right, or threads. In the context of MPI, we would like to call this as processes, and then let us designate one of the process as the one which will receive this hello world message from all other process. So basically all other process will send their message to 0, and then the 0 would try to print it to the screen. Okay, so that, I mean, we would like to do this instead of every process printing its own message. We would like to do this such that there is some kind of a send receive message happening between the process. For example, in this context, all other process other than the 0th process would send some message, and that message is hello from such and such process, and 0 would actually receive all those messages, and then once it receives, it's going to print them to the screen. Okay, so that is the program we would like to write, and of course these process numbers are known as rank of the process. So you can call these numbers as either using some name. You could call it as my rank or my ID, something like that, which would actually tell you what is the rank of the process that we are trying to that we are working with. Okay, so before so let me kind of quickly show you the C version of the program using MPI. That is program hello MPI .c. Okay, so this is basically the program. We will look at each and every line of this and try to understand what it is that it is doing. But before that, assuming that all other process will send the data to 0 process and 0 will print it. So let me try to first compile and run the program. Okay, so compilation and execution. So for compiling the programs, you would use MPI CC as the C compiler, okay, which is basically is called using MPI CC, and then I would have -T -W all. That basically gives you the debug options as well as warn all the messages, and then -O to link the object file. You can say MPI hello. I can say program MPI hello MPI.c. Okay, it compiled. Now if I were to run it, I would use MPI execute -N. Okay, I would like to execute on, let's say, 4 processes, and then I would say /MPI hello is the executable. Okay, so it takes a while. I don't know why on my laptop, and then it prints hello from process ID 1, 2, 3, and 0. Okay, so it has printed. So basically, the 0th process has received all these messages, and then it has printed the messages it has received, and the 0th process itself, which is the designated process for receiving the messages, also prints its own message here. Okay, so it's kind of running here. So let me basically tell you that I am running on my laptop. I installed something known as OpenMPI. This is the open source project for MPI implementation. You can also kind of install this on your laptops, or if you have access to Aqua, you are welcome to run there using the queue submission systems that you are already aware of. Okay, all right, so you can do either of the things. Other implementations are the MPI CH and MPI CH2, which you may or may not want to install depending on the choice. I think they are all installed on the Aqua anyway. Okay, so let me just write down these commands, which is basically for compilation and execution of the MPI program. So basically, how do you compile and run? Okay, so the compilation command is, you have basically MPI CC. So $, is the shell prompt, and you have MPI CC. You have the compiler optional arguments here, which are -G -wall, and then we have a -O to link to the object file. I would say MPI hello, right? So this is the name of the executable, and then we have some name of the name of the program, that is basically program MPI hello.c. Okay, now this command is the same if you have Fortran. So you have MPI F90 -G -all -O. This is the same, and then you have program MPI hello.f90. Okay, and then to run the program, we said you would use MPI execute, right? You can use MPI execute, or you can even use MPI run, right? Or you can use any other command that is kind of depending on the choice of the wrapper that you have, and then you would use -N, and then you would request the number of processes, right? And then the name of the executable, right? Okay, so in these cases, this particular essentially the MPI CC is called the wrapper script. Okay, so what the wrapper script does is it basically calls the C compiler, right? Essentially, wrapper script is one which will basically run a particular program. In this particular case, this MPI CC will run the C compiler as the, it will run the program, which is the C compiler, and then it will basically pass all these arguments to the C compiler, as well as it will also tell the C compiler that where it should look for the corresponding header files and other function definitions, etc. So it kind of points to the required libraries, that are required to compile an MPI program. Okay. Now, of course, MPI program can be run on a single process as well. So, in fact, you should write it in such a way that it will run on one process or on multiple processes. So, if I run it on one process, it should actually just print hello from process ID 0. That's all, right? Okay, that's what it is printing. So, let me also quickly show you the Fortran program I have. Basically, program MPI hello MPI.f90. So, this is the corresponding Fortran program. Again, we will discuss this in detail. So, this Fortran program is basically doing the same thing as what the C program that we have seen. Let me also compile this. This is MPI F90 minus T minus W all minus O MPI hello program MPI hello MPI dot F90. Okay, now it's going to throw some warnings, not errors, so that's okay. So I have used extra comma here, which it says is a legacy extension, so I don't really worry, because I know that it has compiled. Okay, so I would just run this MPI run or MPI execute minus n. I would use 3 process and say dot slash MPI hello, and it's going to print 3 messages from each process. Okay, so basically we got hello from process ID 1, 2, 3. Okay, you can see that this is coming from a different slightly looking different, so it's basically coming from this latest compiled executable from the Fortran program. Okay, it is not running the same C program that we had before. Okay, that is kind of is good news. So the program Fortran program is also now compiling and running. Okay, so that is how you would basically compile and run your programs. And if you are using a cluster such as Aqua, then you have to follow the job submission rules, and then it will basically run and write the output to whatever the output files are. Okay, all right, so basically your MPI execute command that we have, it basically tells the system, okay, when you use MPI execute, it tells the system to start so many instances of this particular executable, right? That's what it tells you. In fact, it might also tell that which of these processes should get what rank. Okay, so MPI execute kind of prepares. Okay, so because now all we did was we kind of executed the statement, and then we got so many messages, right? We got so many greeting messages. And how did this happen? This happened because MPI execute instructs your system to run number of processes instances, right? If you say 3 or 4, so many instances of your executable, right? So that is how it got it. And then once the executable runs, and the executable kind of, then the MPI takes over and it executes whatever is there inside the executable. That is basically a translation of the program you have written. Okay, so that is kind of the about how you compile and run the programs. Now let us take a look at the MPI program itself that we have written and see what are the differences compared to the regular C program. Okay, so let me first start with C. After that we'll go to the Fortran. So the first 2 test statements are basically same as any other C program. So this is actually a C program, right? We just have some more additional functions which we have written, which are implemented or available in the MPI library. Okay, so the first 2 lines hash include stdio.h and hash include string.h. These are same as any other C program, and this is the new line, that is hash include mpi.h. This is new, and essentially this contains, right, this is new and contains the mpi.header contains the function prototypes as well as any other macros, right, and other variables that are used in MPI programs. Okay, it will contain all of those things, and where to find this is basically in the particular computer will be specified by your MPI CC, the compilation wrapper, right? So that wrapper script will tell you that. Okay, then you have the main function, that is basically a main program, int main, and you have 2 arguments just like any other program, int argc and character ** argv. These will basically be the command line arguments. If you had passed something from the command line, they will be coming into this. And then I declare few variables here, which we call it as integer I, my ID. So we will use my ID to determine basically the rank, right, of the process. If you have process 0, 1, 2 or p-1, that will be stored by my ID. And then size, I would kind of tell you where I use it. And then tag, we have basically some tag variable which is given as 100. Then I declared we declared basically a message send and message receive, which are character arrays of 50 characters each. Okay, so that means the message that we want to send, which is hello world from such and such process, will be copied into this message send buffer, and it will be sent. And similarly, we need a buffer to receive, that is message receive. Okay, and then we have this particular variable called status, which has MPI underscore status. Okay, so MPI status is a data type that is defined in MPI.h or MPI implementation. Okay, so this is a new data type that is available in MPI.h. So this is not coming from C. Okay, this is coming from MPI.h. All right, then okay, let us see here. We have three function calls. If you see, I have something known as MPI initialize, I have MPI communicate size, and then we have MPI communicate rank. Okay, fine, we will see what they are. But for now, let us see that there is a first call which is MPI initialize, and then we have blah blah blah, so many other functions here. And then finally we have something known as MPI finalize. Okay, all right, and then return 0, and then the program ends. Okay, of course I have jumped on between many lines. Okay, we will not look at it immediately, but let us try to first see this thing. That means you have int main program, and then you have MPI initialize, and then a lot of programming statements, and then you have MPI finalize. So this is basically tells you the structure of a of any standard of any MPI program. Okay, so any MPI program will have basically this kind of a structure. So what kind of structure? That is you would have hash include MPI.h, and then blah blah blah, and then you have basically your int main, okay, with some arguments, and then maybe you'll have some declaration of variables. Then you have this call, so that is your MPI initialize, right? That is the MPI initialize call, which is has some arguments. You can pass the ampersand argc and ampersand argv, okay, and then some function calls here, and then finally you have MPI finalize, and then you have return 0, right, and close the main program. Okay, so that means we have these two. So we have included the header file. Then the first function, MPI function to be called in the program is MPI initialize, and the last function to be called in the MPI program is the MPI function to be called last is the MPI finalize. Now these are as a rule of thumb, you should not call any other function, MPI function, before MPI initialize. Similarly, as a rule of thumb, you should not call any other MPI function after MPI finalize. Okay, so your program should begin with MPI initialize and it should end with MPI finalize, and if after this you should not call any other MPI function. Okay, similarly, no MPI function calls before MPI initialize. Okay, so those are the two things. And then what we also see is that there is a particular way you should write your names of these functions. So the names, at least in C, MPI initialize, so all the functions that are provided by MPI, so we're talking about in C, okay, will start with MPI underscore, okay, all the function names, all the function names that belong to MPI. And then after that, the first letter after the underscore is capitalized. Okay, so this is capitalized, so that's why you have MPI initialize. Is it MPI initialize? Yeah. And then we have MPI finalize. Okay, so this is capitalized, this has to be capitalized, and after that it is lowercase. Okay, so that syntax needs to be followed, otherwise C program would throw an error saying that MPI initialize, you know, if you use a different thing, it will not be recognized. Let us try that. So let me just write it as in C, let me write it as MPI initialize and try to compile this program. Okay, see, now it says implicit declaration of MPI. Did you mean MPI initialize? Okay, so this is, did you mean MPI int? It's saying, okay, I don't mean that. So let us go back and change it back to MPI initialize. Okay, that is fine. All right, so that means all the function calls as well as the MPI types should begin with MPI underscore, and then the first letter is capitalized. Okay, and then you have all the variables or macros that are defined in MPI are completely capitalized or completely capitalized. That means completely in capital letters. For example, yeah, so for example here you have something known as MPI word. Okay, so this is always in completely capitals. If you write in any other case, it would complain that this particular variable or macro is it doesn't know what it means. Okay, so for example, similarly you have something called MPI underscore char here, right? MPI char. So this needs to be always completely capitalized. Okay, so that is the rule of the thumb. And then as a result, you can have your own functions, but not conflicting with this kind of naming convention. Okay, so that your own variables or function calls will not conflict with the ones provided by MPI. Okay, so you have to make sure that you are not naming your functions and variables as the same names. So you should use a different convention and different naming thing so that it is not same thing. Okay, now of course let us see what is the syntax for MPI initialize. So the syntax for MPI initialize is, it has basically int MPI initialize, and the argument it takes are, it basically takes int star. It basically takes a pointer to your argc pointer, and it also takes a pointer to your character star, that is basically argv pointer. Okay, that is the syntax. And MPI initialize has a return type of int. This basically has some error code which will tell you about the success of the function call. Okay, so that means by looking at this error code, if you can catch it into some variable, you can know what is the status or success of the function call. But in general, we will not be worried about doing that unless you are writing a very systematic program, or very or a program where you have to kind of debug those things on the basis of the function calls success. Okay, so we would usually ignore, we would not catch this. That's why we don't have it here. I just wrote it here as MPI initialize, right? I did not put it, but then if you want, you can also put another integer and then catch this return type and then see whether it is successful or not. Okay, depending on the error code number. Okay, so that is and then it is also not compulsory that we always pass argc and argp pointers. For example, these are only required if your command line arguments, right? Command line arguments, if they need to be passed to all the instances, right, or to all the processes, right? If you have to be to all the processes, then only we would need this thing, right? If it is not required, then you could actually just pass null comma null instead of argc comma argp. Okay, that is also quite possible. So if that is the case, you would just write, instead of this, you would write MPI initialize null comma null. Okay, that is fine. All right, so that is about MPI initialize. And the MPI finalize is very straightforward. The syntax is basically, if you look at it, the syntax is just MPI finalize, and then there is nothing here. So MPI finalize syntax is can be written like this: This is also has int, okay, and then you have MPI underscore F capital L, and then finalize, and it takes no argument. So this is basically void. Okay, so it tells so MPI finalize, this function call tells MPI, right, to essentially kind of tells MPI that tells the MPI that it doesn't have to, there are no more MPI calls that will be called by the function, okay, by the program. So just like MPI initialize, so MPI initialize, what it does, it basically tells the system, tells the MPI system to let's say allocate any buffer, right, or any memory, right, to send and receive. Also it may tell that, essentially it tells that to get it will basically tell the system to get ready for running the program, right. So that may involve allocation of memory or essentially assignment of ranks, etc. So all these things, all the bookkeeping will be started with MPI initialize. Now once you call MPI finalize, it tells that you can kind of free all the memory that you allocated, because this will not be used anymore, right. Free all the memory allocated by MPI system, right. Similarly, no other MPI function calls will be allowed after this, right. So that's what basically the MPI finalize tells it, and then as a rule of thumb, you should not call any other MPI function after this function call. Okay, you can call any other functions if you wish, but not an MPI function call. Okay. All right. Then okay, that is about the MPI initialize and MPI finalize. Then let us move on to the other statements in the program. So if you see here, what we have is MPI. There are two more function calls. This is MPI communicate size and MPI communicate rank. Okay, both are taking an argument as MPI communicate world, and then the second argument is passing an address which is size, and here it is my ID. Okay, so as the name suggests, the function call MPI com, C is capitalized here, and the second this S should not be capitalized actually, right. Only the first letter after the first underscore after MPI should be capitalized. So MPI communicate size basically is a function call in which it will tell, it will basically fill how many processes are there, and that will be returned in this argument size. Okay, so basically this one, this function call tells about the number of processes that are there. That means if the size will basically tell you how many processes are participating. If you had run this program with 4 or 3, it will basically return 3 or 4, okay, depending on how many processes are running. And then MPI com rank would tell, basically will return the rank or ID of the process that called it, right. For example, if particular process calls it, it will tell, okay, my ID is 2, my ID is 1, and so on. Okay, and then you see that the first argument here is called MPI communicate world. Okay, so MPI communicate world is basically a macro or a variable that is defined in MPI.h, and this is MPI com world is basically of the type known as MPI communicator. If I would like to write it here, so MPI com world here will be of type a new type called MPI communicator. And what this basically tells is, it basically is basically a communicator, right, or we can call this as the default communicator that MPI provides. And what is a communicator? A communicator is basically a set of processes, and a set of processes is kind of comprises of a communicator, and these processes within a communicator can talk to each other, right, by using or by means of send receive commands. Okay, that means a set of processes in this particular instance, MPI com world contains all the processes that we have started. If you have started 4 processes, that means 0, 1, 2, 3 being the ranks, right, or my ID in this particular case they can all talk to each other because they all belong to MPI com world, okay, by default. But there will be some instances in a complex programming, you know, requirements, you would probably have to make your own sets of processes to belong to a different communicator. Okay, so in such instances, then what happens is that then a set of processes in a particular communicator can only talk to themselves, and then another set of processes in another communicator can only talk to themselves. Okay, so this kind of thing is probably required in some instances to speed up the performance of the program. Okay, we will probably see if there is an instance we will talk about this thing, but as of now we can see that we can say that MPI com world is a default communicator that is provided by MPI system, and then essentially it contains all the processes that we have within the program. Okay, all right, then what we notice is that we basically look at MPI com size and MPI communicator rank here. Okay, so that is what these two functions calls are about. Then what we realize is that now this program now has a bunch of if-else. We basically have a bunch of statements which within an if-else statement, right? So in this is what we're trying to do here is that if my ID not equal to 0, that means if you are not the designated, right, process to receive, right, you just need to send the data. Because if you remember, what we did was we said my ID equal to 0 is the one which will basically receive all the data and then print them, and all other processes will basically send the data, right? So that means RECEI. Okay. Okay, so all right, then so what we have is okay, so if your ID is not equal to 0, then what we are trying to do is we are sending hello, so from process ID, okay, and then my ID. So essentially this particular statement will be executed by all the processes, right? Now all the processes will execute the statement, and then once if statement is executed, once you come here, only all other processes other than 0 will execute this statement, right? sprintf is basically printf to a particular string, and the string we are printing to is called message send, right? That's a character array, and that is basically is the message we want to send. And then what we are sending hello from process ID and some number. Okay, now this will be executed by 1, 2 and 3 if you are calling, let's say if you are executing with 4 process. Then this particular function called MPI send will send this data. Okay, again you would notice that MPI underscore is capitals and S is capital and E and D is lowercase. Will send this data, so this is basically message send, and then we are sending 50 values of this particular data type character. Okay, and then there are other arguments here. We will come to this thing. Okay, so there are certain arguments here. Number of arguments is basically 1, 2, 3, 4, 5, 6. So there are 6 arguments, right? And then MPI send is sending it to the 0th process. Okay, so this 0 is basically what it is tells it to send, right? So this is basically the destination. Then in the else statement, that means this will be executed by whom? This will be executed by only by process ID equal to 0, right? That means only my rank equal to 0 or my ID equal to 0 will only execute this statement. So now how many MPI sends have been executed? 3. If you are running a program with 4 processes, 0 is not executing this statement. So 1, 2 and 3 have already sent their data through this MPI send. That means 0 now has to receive 3 messages. That means unlike MPI send, which is written only once here but executed by 3 processes, we would need a loop for MPI receive, so that it will receive on 0th process, it will receive one statement from each of the corresponding sends. Okay, so we would need to balance the sends and the receives So I have a loop here for I equal to 1, I less than size I plus plus. So I'm going to receive from process ID 1, 2 and 3, right? Here size is basically is set to 4, right? That's what it will be once you run it with 4. Then let me put this. Okay, then your MPI receive will receive the message into message receive, and it will again receive MPI char, that is MPI characters of 15 length, and I is basically the one tells you that receive from such and such process. So I equals 1 will tell that receive a message from process 1, I equals 2 will tell that receive from 2, and so on, and there is a tag, and then there is MPI convol and ampersand status. So there are now unlike MPI send, there are now 1, 2, 3, 4, 5, 6, 7 arguments. Of course the first 6 arguments are the same as what we have for MPI send. Okay, so I'm going to write down what these arguments are in a little while. Okay, and what is the syntax, and then once it receives, it's going to print the data to the screen. So basically the process 0 is receiving message receive, and that whatever it has received, it is printing to the screen using printf. Now once it is done receiving and printing the data, the process 0 itself is printing its own hello message, its own greetings, and then into the message send, and it is printing the message send. Okay, so that is about the program. Now what you see is that, and then of course you have MPI finalize. Now what you see is that this particular if else statement is making our program into to be executed differently on different processes, right? That means we have written a single program, but the behavior of each of the processes in executing this program is determined by this if else statement, right? Because of this if else statement, our program behaves differently on different processes or different ranks, and that's what it makes the program to be like a SPMD program. That means single program, multiple data. Okay, so if I were to write this, so we have now seen this as a we have only written single program, okay, multiple data. So this is known as SPMD program, and in this particular example our if else statement makes or converts our program into an SPMD program, right? Because that is what is making it to behave, that is what is making it the process to behave in a different way depending on the conditions here. That means we did not write different programs and then we didn't compile different programs, right? We only compiled a single program, and then it kind of behaves differently. Okay, so that is the beauty of the MPI programs. In fact, all the MPI programs that you will come across, whatsoever complexity they are written with, they are always written like this. You will basically have a single program, and then depending on the based on the by the use of a clever use of all the statements, they are going to behave differently and then accomplish the task that is required. Okay, all right, then let me quickly write down the syntax for MPI send and MPI receive for C. Okay, once I finish this, I will also show the corresponding Fortran program. So the MPI send has the following syntax, right? So this is, it has just like any other MPI function, it has a return type, that is the error code MPI send initial capitalized. Then the first argument is the pointer to the message buffer. So we have some message buffer pointer, and then the next argument is the message size. Okay, the size of the message, and then the third argument is MPI data type. Okay, and then you have the message type. Then the third argument or fourth argument is basically the destination rank to which this message has to be delivered. Okay, and the fifth argument is int tag. Okay, and finally the last argument is the communicator, which has MPI communicator as the type, and then the communicator. Okay, so now let us try to see a one-to-one balance. So MPI send is basically the message buffer. So the first three arguments are related to the contents of the message. right? That means what is the what is the what is the address of the message that needs to be sent, where it can find, and then what is the size, how much should I send, and what type, right? Should I send 5 integers, or should I send 5 integers, or should I send 3 characters, or what should I send? That is what is basically defined by the type and the size. Now just because you cannot pass the type as an argument in C, MPI has to come up with its own data type, so that the type can be passed, right? Because you can only pass a variable of a particular type in C, you cannot pass the type itself. So that's why MPI defines MPI data type, which is basically very similar to what you have with a MPI underscore int would be MPI integer, MPI underscore char will be the character, and so on. You can look this up in the MPI reference manual. Okay, and then that is about the first 3 arguments, and then the last 3 arguments are about the destination, right? Destination to where the message needs to be delivered, right? Okay, that means this destination is the rank of the process, right, to which the message has to be sent, and this particular tag here, this tag is a number that should be the same. Basically this tells you for matching the messages. That means if there are more than one message received, then this particular tag will be matched in order to copy the correct values. Okay, and then the communicator tells that which communicator should I look for to find this particular rank of the process, right? Because multiple communicators might be available, and in this particular simple case we are using MPI communicate word. Okay, so that is MPI send. Now let us look at the MPI receive. So in the MPI receive we have integer as the return type, that is the error code, and we have MPI receive. So the first 6 arguments are the same as what are there in the MPI send. Okay, only thing is that the few things will differ, but they are pretty much the same. So we have void star, okay, message buffer predicate, sorry, message buffer pointer, right? And then you have int, what is the message size, right, or the buffer size, and then you have MPI data type, so that is the message type. Okay, and then we have integer. So just like before, the first 3 arguments are basically related to the contents of the message, right? That means this message buffer predicate basically tells where to put the message that is received, and what is the size of the message that is received, and what type. So if you are receiving character messages of 50 characters, or 5 integers, or 3 floating point numbers, that is what will be defined here. Okay, then we have int. Here earlier it was destination, here now it is source. So what is the rank of the process or the source from which I should receive the message? Okay, that needs to be clear here. Okay, and then we have int tag, again to match the tag so that the correct message is coming into the correct location. And then you have the communicator, this is MPI communicator type, you have the name of the communicator, and then we have the status, MPI status star, you would have some pointer to the status. Okay, so this has 7 arguments, again similar to MPI send. The first 3 are related to the contents of the message, and then the last 3 are related to the basically the destination, right, or basically the source from which we are receiving, right, source data. Okay, and then The last one regarding status is again a particular variable which is defined using a structure variable, that is MPI status. This is again defined in, just like MPI communicator, this is defined in MPI.h in the header files. We will talk about this little later. Okay, so that is kind of the is the function prototypes for MPI send and MPI receive. Okay, so now let us see if we can match these in the program that we have, which is here. Okay, so this sprintf is nothing but printing it to the message send. Then MPI send, we are giving message send is basically the, because this is a character array, right? Message send is the, if I go back, this is basically the character array, character message send 50. So if you say message send, that itself is the address, so we are sending this address so that, you know, MPI send can look for the data, and then we are sending 50 is the number, is the size of this of the message, and then we are sending 50 characters. So instead of writing char, here we are writing MPI char. Okay, and then 0 basically tells it that send it to 0th process. That means we are sending it to the designated process 0. If you want to send, everybody has to send it to 1, then you change this to 1. Of course, you need to also change here to 1, right? Because you want to designate 1 to be the host process, right? Or the process which should receive the messages. Now we are sending some tag, and this tag is defined as 100, and that is what will be used in matching the messages. We will come to that little later. And then the MPI communicator is the default communicator, that is all capitals MPI com world. Okay, so basically we are sending the message, so all the processes other than 0 are sending it. Now MPI receive is executed in a loop. Here you see the difference here, why it should be in loop. And then MPI receive again starts with R is capital here. Then you are receiving the message into a new buffer, that buffer is message receive, and then you are receiving, now the amount of data you are sending here should be balanced here. We will also discuss later more about this thing. For now it is 50 and MPI character, MPI char. Then here I is basically the source from which it should receive, right? So MPI receive should receive one statement from process ID 1, one from 2, one from 3, right? So that's why it should receive from, I goes from 1 to 3, so that is what it should be, right? So it should be receiving, because they are sending it here, it should be receiving from 1 to 3, and then this tag should be the same as what you had here, so that is the same. Then MPI com world, and then you have ampersand status. This is basically your of a data type defined as MPI status. Okay, all right, then you are printing the messages, and then of course it's printing and finalize. All right, so that is the program. Let us look at the corresponding Fortran counterpart of it. Program hello MPI.f90. Okay, so just like before, we have program main int, and then this is the new statement, right? So the new statement is include MPI f.h in double quotes here. That means MPI Fortran.h. Okay, that will basically contain all the required function prototype definitions and macros and all other variables. Then I have these variables, I, my ID, size, MPI error tag, and then status is now an array with MPI status size. Okay, all right, then character, we have two buffers, that is message send and message receive, which are basically character arrays of length 50. Okay, just like C, we have call MPI initialize. Now in Fortran, you don't have case sensitivity, so it doesn't matter how you write it. If you write it MPI initialize all caps, all lowercase, or any variation of mix and match of lowercase and uppercase, everything will just runs. Only thing is that you will never be able to have another function as a lowercase or any other thing, right? So that is kind of probably an advantage, or could be a disadvantage depending on the situation. So you have call MPI initialize, and then we pass an argument MPI error here, which is the integer. Okay, then similar to C, we are basically calling this instead of C. Unlike C, you basically have to write call here to call the function. So you have MPI communicate size, and then this is the same as before, MPI communicate world. And then unlike C, we are sending this MPI error with each and every call. So what you see is that you have one argument extra compared to all the function calls in C, right? So basically you have MPI com world and then size. So size will contain now the number of processes that are launched by the program. and then MPI error would contain some error code if it is unsuccessful. So this MPI error earlier in C was basically it was there in the return as the return value, right? Now in Fortran, for subroutines, you don't have a return variable, only for functions you have it. So as a result, they have put MPI error as an argument here. Okay. Now if you want to look for the code whether this particular function is successful or not, you have to look at observe what is there in this MPI error after the function call is over. Okay. Similarly, you have to get the rank of the process, you call MPI communicate rank, and then you have my ID. So my ID basically would be the rank of the process. Then you fill the tag equal to 100. Then you basically do the same thing what you have done in the C program. If my ID is not equal to 0, you write the message send, and then you send it to 50 characters of MPI character, send it to 0th process with some tag and MPI communicate word. Okay. And else, if you are not the process, if you are not the process 1, 2 and 3, then you receive it, and then you need to receive as many non-zero process you have. That means do I equal to 1 to size minus 1, call MPI receive, you receive in MPI receive, again MPI character 50 MPI characters, and then receive from 1, 2 and 3, and then the tag you have to match is tag, and MPI communicate world is the communicator, and then status contains essentially some data related to what is being sent. Okay, we will come to this little later. And then you write the message, and then you basically have MPI finalize. Okay, so that's the program. I don't know if I had compiled. I think I have already compiled this and shown it, right? Okay, I have already compiled. So you could kind of also try running this program on your local computer or on the cluster if you have access to it. Fine. So that is in a shell about writing a simple hello world program in which the messages from different processes are sent to a designated process, in this particular case as process 0, and then the process 0 will print the data. Okay, will print the message that is received. And we have also looked at the standard function calls, which are MPI send and MPI receive, and how MPI programs are in the single program multiple data kind of paradigm. Okay, all right, so I'm going to stop here. We will look at more at the other things, other aspects of these MPI send receive, and go into further details in the next lecture. Okay, all right, thank you, talk to you later.